So today we're going to review some properties of functions, and we have seen similarly in lots of other examples in math, but frequently we relate one quantity in terms of another quantity. So letter grades in math depends on the numerical score, the amount you paid for gas depends on how much gas you got, the average amount of money you spend depends on what you were buying. Lots of different things have relations to one another. So we have an ordered pair. And it puts two variables, x and y, together because they are related to each other in some fashion. X is the independent, it's the thing you plug in, it's the input. And y is the dependent variable or the output. So anytime two things are related to each other, no matter how they're related, they are a relation in mathematics. Even like my 12th cousin down my family line is still related to me in some fashion. So most everything in math is a relation, but not every relation is a function. Being a function is a very special category. So if you're a function, there's exactly one value, one x that goes to a y. So each input, I'm going to put this in other words, each input, which we oftentimes call x, only goes to or is paired with exactly one y value, which is our output. So in other words, you were told a lot of times in Algebra 1, lots of times, x cannot repeat. So if we look at this set of ordered pairs that I'm underlining in blue, this is a relation. 3 is somehow connected to 10.5, 8 to 28, 10 to 35. It's also a function because 3 only shows up once, 8 only shows up once, and 10 only shows up once. So this relation is a function. So let's use what we know about functions and figure out whether the things we are given are just a relation or if they're actually a function. So if we look at set F, it says 1, -2, 3 for my x's, so none of my x's repeat. So this is in fact a function. And if you look, this -2 goes to 4 and the 3 goes to 4. Right here you can see the drawing of it. But that's okay. X's can go to the same y, but the x cannot go to two different places. If we look at letter G, I just read the x coordinates to myself. 1, 1, 1, and you should stop. Because you have said the same number for x more than once, x repeated 3 times in fact, so this is not a function. Let's look at letter F. So I have -4, -2, -2. Oh, these two, look right here. They repeated, so this is not a function. And to see a visual of that, this -2 went to two different places. You can't do that, guys. You as a student cannot go to two classrooms at one time. It doesn't work, so those are not functions. So something we talk about a lot with functions is domain and range. Domain is the x, range is the y. If you have problems remembering that, they go in ABC order. So domain came first, so domain goes with the x. Range came second in alphabetical order, so range goes to the y because the y comes after the x. Another remember it was an acronym called Dix-Roy, and that stands for domain, input, x, range, output, y. So in the next problems, it says find the domain and range of each. So a good rule of thumb when you're writing domain and range is that you put things in numerical order and they don't have to repeat. So domain is my x's. So my domain would be 3, 4, 4, 6. I repeated the word 4, so I don't have to write it twice. 3, 4, 6. Range is the y's. So -1, 2, 5, 8. -1, 2, 5, 8. For the next one, these are the things I'm plugging in. These are the inputs, and they're going to the outputs. So my domain is my inputs, my x's. So my domain is 4. Good rule of thumb is to write them in numerical order. So the -3 at the bottom, -3, 4, 6, 7. My range is the outputs or the y's. 100, 200, 300. For letter C, domain is the x's. So -5, 0, and 5. Range is the y's. There's only one number in there, so you only have to write it one time, 2. So on the next page, we're going to give it the domain and range of each of these. So zoom in. Remember, when you do these, ordered pairs are x, comma, y. Actually, let me color code that for you. The x's are blue, and the y's are, oh man, the y's are all in red. So the first part of the ordered pair is all my x's. And when we read x's, it's a left and right movement. So read from the left to the right this way. So my domain is -1. Actually, let me not draw dots. Here's my -1, 0, 1, 4. My range is going to be the y's. So for range, read from the bottom up to the top, because range is a y thing and y's go from the bottom up to the top. So my very bottom right here is -3, comma, -1, comma, 1, comma, 2. The next one, a little bit different. So domain is left and right. So if you can look at a graph and find the left-hand side and find the right-hand side, then that's my domain. So my domain on this one started at, we're going to put a bracket because I actually touch -4, and I go all the way across this way to +4 with a bracket. With range, we want to go from the bottom up to the top. So the very bottom down here was -6, and the tippy top right here was 6. So my range, and I touched -6 and 6, so my range is going to be -6, comma, 6 with a bracket. When I get to letter C, I have a problem. On letter B, I drew a left and right, but I can't draw anything because this graph is going to keep moving to the left and keep moving to the right forever and ever. So since my graph doesn't have an end point on the left or on the right side, its domain is all real numbers, which we can write as -infinity to infinity. Infinity symbols always get a parenthesis, never a bracket. A bracket means that you can actually touch it. you can't touch infinity, because if you say infinity, I'm going to say infinity plus 1. Infinity just keeps going forever. With my range, this graph is going to keep moving down in this direction, but it's still moving up in this direction too. So for my range, it's also all real numbers, or negative infinity to infinity. One more problem on the next page. Here's a parabola, nice little U. So this graph, if I go to find the left or the right side, this graph is going to keep moving. Yes, it's going up, but it's still moving in general to the left. And this piece is going to keep going up, which is up, but it's also slowly moving to the right as well. So my domain, negative infinity to infinity. My range, however, I do have a very, very bottom. Here's my very, very bottom, and it's -3. So for my range, I touch -3 and go up, because the graph goes up forever to infinity with a parenthesis. So just we're all on the same page, agreement on domain. Unless otherwise specified, the domain of a relation is assumed to be all real numbers that produces real answers when substituted in for a variable. So let's reword this. Unless there is some restriction the domain is any and all x values that you can plug in to get out an answer. Okay, the vertical line test is where you draw vertical lines. Vertical means up and down. You're going to draw vertical lines. And the rule is you can only touch any one, no, let's not use that word twice again. Any vertical line one time. We use the vertical line test to figure out if we're a function or not. So let me draw an example. Let me draw two actually. So I have these two graphs. On the first one, when I draw vertical lines, each one of the lines only touches the graph one time. So this would be a function. But on my circle, or my oval, because I can't draw, the vertical lines touch more than once. So that is not a function. So we're going to use the vertical line test on the next problems to see if I'm a function or not. And they actually already drew them in for you. Super nice. I'm just going to highlight them. So this vertical line right here, it only touches that one dot. This vertical line only touches one dot, and one dot. So this one is a function. On the next problem, B, I touch twice. So this is not a function. On the next one, I only touch one time, so this is a function. And letter D, it's a function. So now we aren't given a picture, and we're going to determine whether what we're given is a function, and then we're going to give its domain and its range. So since we aren't given a graph, we have a couple options. So option 1, we can draw a graph. Option 2 is that you plug in a x value and you should only get out one y value. So let's start with letter A. Letter A, if I do attempt number 2 that I wrote over there, y equals, you can pick any number you want for x. We'll pick 2, whatever, it doesn't matter. 2 plus 4 is always 6. I plugged in 2, I got out one answer, 6. So yes, it's a function. Another way you can do it is you could draw a graph. Hopefully you know that that's a line. And the y-intercept is 4. And the 1 right here is my slope. So I go up 1 and over 1. So there's another dot. So here's my line. And if I do the vertical line test, it's also a function. So no matter which way you do it, this is a function. Using your graph, you can see that your domain, all real numbers, negative infinity to infinity. Your range, also negative infinity to infinity because the graph goes up and down forever. If we try letter B, I'll do version 2 first. Let's see. If I plug in we plug in 5. Y equals square root of 2 times 5 minus 1. That's the square root of 10 minus 1, square root of 9, 3. I plugged in 5 and got out one answer, 3. So it's a function. We can sketch a graph. To sketch a graph and find some points is a little bit trickier in this problem unless you know what your parent functions look like. So see if I can help you out a little bit. I have a square root in my problem. And the first thing that we know how to square root without making I and those imaginary numbers show up is 0. So 2x minus 1 needs to equal 0. If you add the 1 over and divide by 2, you get x equals 1/2. So the first number you can plug in is 1/2. When I plug in 1/2, I get 2 times 1/2 minus 1 square rooted. And that's going to equal square root of 0, which is 0. So if I plug in 1/2, I get out 0. We also plugged in 5 earlier and got out 3. So 1, 2, 3, 4, 5, up 3. So this is a square root function that looks like this. Then you can draw your vertical lines to prove your function. If I want to find the domain, it's this math right here that is key. I found the first x value that I can be. So my domain says my very first x that I can ever be is 1/2. And I can plug in anything bigger than that because that will cause the stuff under the root, the radicand right here, it'll cause it to be positive. Well, you can square root any positive number. They're not all perfect squares and pretty numbers, but you can square root any positive number. My range comes from this right here. When I plugged in my first x value, my 1/2, my y value was 0. And then you can see in the graph, I start here at 0, and then I am working my way up. So my range is 0 to infinity. Okay, continuing the same example. I specifically want to do letter C with the solving for y. So I'm going to put a square on the paper. Because I made the root appear, I have to deal with a plus and minus. So y equals plus or minus the square root of x. So if I plug in a number in, like if I let x equals 4, y equals plus or minus square root of 4, y equals plus or minus 2. This is not unique. There are 2 answers that came out. So this is not going to be a function. Let's draw a graph. Normally, when you have y equals x squared, you would draw a parabola like this. Oops, like this. But now I have x equals y squared, which is a sideways parabola, like this. If you didn't know that, you could absolutely plug in points. You could plug in we plugged in 4, and we got out plus and minus 2. So if I go 1, 2, 3, 4, here's positive 2, and here's negative 2. Square root of 0 is 0. So there's my sideways parabola, and you can see it's definitely not a function. For my domain, we can see that I start here at 0, and I move this way. So my domain is bracket 0 to infinity. My range, this side is going down forever. This side is going up forever. So my range is going to be negative infinity to infinity. Okay, on the next problem, this is a linear function, but it's an inequality. So if we graph it, the y-intercept is negative 1. The slope is 1. It says y is less, so we would shade below. So it passes the vertical line test, but it's not a function. And here's, so I pick a dot for my inequality, like this dot right here. It's in my solution set. Its ordered pair is 1, negative 1. And then I have y is less than or equal to x minus 1. Negative 1 was my y value, less than or equal to 1 minus 1. Negative 1 is less than or equal to 0. That's true. That's a true statement. I can pick another dot, maybe another dot down here. It has the same x value of 1, but maybe now it's down 3. And that's also going to work out to a true statement. Negative 3 is less than or equal to 1 minus 1. But now what's happened is I've made my x value repeat. And so because my x value repeats, it is not a function. We have to do to the domain and range. The domain, it's a linear function, so it's all real numbers. And its range, also a linear function, so its range is all real numbers. The last problem is rational function, which you may or may not remember from Algebra 2. But let's talk about let's do domain first. So if we think about these x's right here, that x is in the denominator, and I never want to divide by 0. So what value of x is going to make that bottom equal 0? In other words, x minus 1 can never equal 0 because it's in the denominator. Well, that means that x can never, ever, ever equal 1. So my domain is negative infinity to 1, union, then you jump over 1 and go from 1 to infinity. So you never actually equal 1. If I do my range are the things that come out. So I have a fraction, has a numerator and a denominator. So the only way to make a fraction ever actually equal 0, because I can put different things in the denominator here for x. I can make the bottom become a negative. So I can do like 5 over a negative, which would make a negative. I can do 5 over, and I could plug big x's in, like 6, 7, 8, 9, bigger, and that would be x over, or 5 over a positive, which is going to equal positive. So I can be positives, I can be negatives. I just need to test to be 0. So if I'm going to make a fraction equal 0, the numerator divided by the denominator is going to equal 0, and that means the numerator had to be 0 because we can't divide by 0. But my numerator is 5. I can't make 5 magically become 0, so this fraction, my y equals fraction, is never going to equal 0, which means my range is negative infinity to 0, union 0 to infinity. I can make that fraction negative, I can make that fraction positive, but I cannot make that fraction become a 0. So we know that this graph never, ever, ever has x equals 1, and never, ever has y equals 0. And this is what a rational function looks like, something like this. But it's going to pass that vertical line test. And there's no values that I can plug into that fraction anyways that would repeat. Every time I plug an x in, I get out a unique y. So yes, it is a function. Okay, so we have been talking about what is and isn't a function, and there's lots of different ways to think about what is and is not a function. So number 1 says a function is a relation in which for each distinct value of the first component of ordered pairs, there is exactly one value of the second component. That means every x has to go to only one y value. So number 2 says a function is a set of ordered pairs in which no first component is repeated. So that's what I've been saying, is that no x can repeat. Number 3 says a function is a rule of correspondence that assigns exactly one range, one y value, to each distinct x value. That means every x goes to only, again, one y. So when we talk about functions, instead of writing y equals or x equals, we often use what's called function notation. And we write that y equals f of x. So this statement, f of x, is written f of x or f at x. So we're going to use function notation to evaluate. So if we look at letter A, it wants me to do f of 2. So I need to go to the f function. And the f function says f of something equals negative something squared plus 5 times something minus 3. And so it was f of x equals negative x squared times 5x. But now, instead of having x's, I have a 2. So f of 2 equals negative parentheses 2 squared plus 5 times 2 minus 3. 2 squared is a 4, and then it becomes a negative with a negative out front, plus 2 times 5 is 10, minus 3. Negative 4 plus negative 3 is negative 7, plus 10 more equals a total of 3. So we can write that f of 2 equals 3, or we can say f at 2 equals 3. That results in the ordered pair of I plugged in 2 and I got out 3. Letter B, very similar. So I'm going to write the function down with my blanks in it. F of something equals negative parentheses something squared plus 5 times something minus 3. And that something I'm going to plug in is a q. Q, Q, Q. So f of q equals q squared is called q squared, then you make it negative, plus 5q minus 3. The last problem changes. It's not using f anymore. It decided to use g, and here's my g function up top. So this is going to be g of something equals 2 times something plus 3. It was that this was an x and an x, but now it's not an x. A plus 2, or a plus 1. A plus 1. A plus 1. So g of a plus 1 equals, you should distribute the 2 into the parentheses, 2a plus 2, then plus the 3 at the end. So g of a plus 1 equals 2a plus 5. So now that we know how to evaluate a function, let's go through and evaluate functions in some various ways. Maybe not exactly like we were just doing. So next example is very similar to what we were just doing. F of something equals 3 times something minus 7. The something I want to plug in is a 3, so f of 3. F of 3 equals 3 times 3 is 9 minus 7. So f of 3 equals 2. Every time I'm doing f of 3, so on letter B, it's normally f of x, but now they're asking me to do f of 3. So my x's are 3's. So I'm looking, that's not a 3, that's not a 3. Oh, that's a 3. So when f of 3, when I plug in a 3, I get out a 1. Next one, I'm still doing f of 3. F of 3, so you need to go to your domain, the things you plug in, the inputs, and you find 3, and it travels to 5. So f of 3 equals 5. On the graph, I need to do f of 3. Remember, this 3 is an x, so you go to your x-axis, 1, 2, here's 3. So you go up to your graph, and then I want to find the y value, so I go over to the y-axis, and it's 4. So f of 3 equals 4. So we want to write something in function notation. We need to make sure that we first have a expression or an equation that says y equals, and then we just replace the y with f of x, or any function name, h of x, g of x, j of x, k of x, whatever. So since this one is already solved for y, it says y equals, I can just write it as f of x equals x squared plus 1. No big deal. The next one, got to solve for the y first. So I'm going to move that x over. Divide everything by -4. So I'm going to write y equals, and I'm going to divide everything by -4. So I have 5 over -4 minus x over -4. Sorry, that's equal to y equals -5 over 4. A negative and a negative are make a positive, so plus x over 4. And now we don't want to write y. We want to write f of x equals -5 over 4 plus x over 4. Okay, in this part, we're talking about functions and describing them. So in the first one, we're going to talk about increasing. So if I am increasing, getting bigger, x1's dot right here is only so tall, but my next dot, x2, is way taller. That means that my y values, as I go in order from x1 to x2, they're getting bigger. If I were to go over here to x3, it'd be even higher up. So that's one way to look at it. Another way to look at it is that you can do the following, and I'm going to zoom in for you. You can draw itty-bitty tangent lines. Tangent means you touch it in one place and go away. And so if I were to draw these itty-bitty tangent lines right here, each of these individual lines that I'm drawing have a positive slope, which means the graph is increasing. Same idea. If I go over here to my next graph, you'll see at x1, I'm super tall. But at my next x, called x2, I'm much lower. So the y values were going down. Or you can, again, draw your little tangent lines, and all of these little lines that I'm drawing, they all have negative slopes, so it's decreasing. The last one, there's no change. So at x1, I'm at a certain height. At x2, I'm at the same height. That means there's no change. It means it's constant. And if you draw a horizontal line, the slope of a horizontal line is 0. It is constant. It is not changing. So using what I just described, we're going to go down here to the bottom, and we're going to tell me where am I increasing, decreasing, and constant. So on this graph, all of these little lines that I'm drawing, they're going down. So this part of the graph is decreasing until I get right here to this dot, because then I'd have a horizontal line. So I am decreasing. The graph goes on forever, so I'm decreasing from negative infinity all the way until I get to this x value, -2. When we write these, we are writing open intervals, which means we're only using parentheses, never a bracket, and they are intervals, so from one x value to the other. And so it says intervals of the domain, which means intervals of the x values. If I move on, all of these lines that I'm drawing right here in blue, those are all positive slopes. That means my graph is increasing. So starting from my black horizontal line of -2 and going all the way up to here, I am increasing, which is x equals 1. My graph is constant at this piece right here. So I am constant from 1 until infinity because the graph keeps going in the right direction. So now we're going to use that information and interpret the situation given. So it says the graph shows the relationship between the number of gallons, G of T, of water in a small swimming pool after T hours. By looking at the graph of the function, we can answer some questions about the water level of the pool at various times. For example, at time equals 0, so here's time equals 0, the pool is empty, it has no water in it. The water level then increases for a while, increases, stays constant, decreases, then becomes constant again. Use the graph to respond to the following. So I'm going to see if I can color code this for you. So we'll do letter A in red. What is the maximum number of gallons of water in the pool? So here's my highest point. So the maximum amount of gallons is 3,000. And then it says, when is it at its maximum? So I'm at 3,000, starting at 25, and I stay at that exact same height until 50. So that happens from 25 hours to 50 hours. Letter B we'll try doing in green. For how long is the water level increasing, decreasing, constant? So here's my increasing piece right here. So I'm increasing, and that's a span of, starts from 0 and goes to 25. So I'm increasing for 25 hours. I'm going to erase my green, so I have to draw again in a second. So erase the green. And then it says I am decreasing. That means I'm going down. This piece is decreasing. So I start decreasing at 50 and I stop decreasing at 75. So this span of time right there is 25. So I'm decreasing for 25 hours. Again, I'm going to erase my green really quick so I can draw with green again. And then it says, and constant. So this length here is constant, which we know is from 25 to 50 hours. We did that in part A. So constant, the first piece is 25 hours. But that's the only piece of being constant I have. I also have another piece down here from 75 to 100, which is another 25 hours. So if I do that together, it's a total of 50 hours of being constant. How many gallons of water are in the pool after 90 hours? So 90 is right here, up here, and then I go across like this, and the answer is 2,000 gallons. Then it says to describe the events. So I start at time equals 0, and my graph goes up. So let's say, I'm going to write above it so I can fit it and see the graph. So after time equals 0, we begin to fill up the pool, period. So it takes me 25 hours to get to the max to fill up the pool, comma, we'll change my period to comma, which takes 25 hours. Then I'm constant from 25 to 50. So maybe we finished filling up the pool, and because it took 25 hours to fill up the pool, now I have to wait for the pH balance or the chlorine to sit and do its business. So then the pool sits. So the pool sits constant, undisturbed, no one's in it. For 25 hours. And then maybe after that, people start playing in the pool. And you know when people get in a pool, they jump around and water comes out. So people play in the pool for another 25 hours and the water goes down. So people play around in the pool, thus the pool's losing water for 25 hours. And then finally the pool closes or whatever happens, and now the pool's new level is at 2,000. But anything of that nature would explain what occurred to the pool. So now you can go do your 2.3 homework.